Hello students, today's topic is basic and derived quantities and their units in physics. A physical quantity is a physical property characterizing some aspect of nature that can be measured or calculated. For example, time, temperature, velocity, energy are just a few examples of physical quantities. These physical quantities are usually expressed by symbols. They have a number which is showing the magnitude. For example, when you say the length of a pen is equal to 15 in numeric value, but we have a unit you measure, for example, centimeter. So you can say the length of my pen is 15 centimeters. We have in general two types of units. One, the fundamental units, and the second one is the derived units. The fundamental or the basic units are those that are unique and cannot be derived from any other units. But derived units are expressed algebraically in terms of fundamental units or other derived units. The symbols for derived units are obtained by means of the mathematical operations of multiplication and division. They are derived from other derived units or fundamental units. These are the fundamental units. We have 7 of them. The first one is the mass. The unit of mass is kilogram, the symbol kg, and we use equilibrium balance to measure mass. It's the amount of matter in an object. The second one is the length. The unit of length is meter, the symbol small m. We use meter stick or ruler to measure length, and it's the one-dimensional extent of an object. The third one is time. The unit of time is second. We use small s. We use stopwatch or chronometer to measure time. It's the duration of an event. The fourth one is the current. The unit of current is ampere. We use the capital A. We use ammeter to measure electric current. It's the rate of flow of electric charge per unit. The fifth one is the temperature. The unit of temperature scientifically is Kelvin as a basic unit. The symbol is capital K. We use thermometer to measure temperature. It's the average kinetic energy of particles in an object. The sixth one is light intensity. The unit is candela. The symbol CD. We use photometer to measure light intensity, and it's the amount of energy emitted by a light source in a particular direction. And the last one, which you will usually use in chemistry, is the amount of matter, the mole. The symbol is MOL. There's no tool to measure the mole. Mole is the number of particles compared to the number of atoms in 0.012 kilogram of the 12 carbon isotope. So you have to know these 7 quantities. These are the fundamental units, and all of the others are derived. Now here we have the derived units. The table below gives the SI, which means the International System of Units, derived units. Area, for example, the unit of area is square meter. How you get it? You multiply meter by meter, so you get the meter square. The unit of volume is cubic meter. How you get it? You multiply meter 3 times, so you get the unit meter cube. Speed or velocity, the unit of it is meter per second, so you divide meter to second. The acceleration, the unit of acceleration is meter per second square, so you divide meter to second 2 times. The density, kilogram per cubic meter, so you divide kilogram into meter 3 times. So you see that there are divisions and multiplications. So we have mathematical operations, so they are derived from the other fundamental units. There are some derived units which have special names and symbols. This is just for simplicity for use. For example, the frequency, we use hertz. In fact, hertz is equal to 1/2 second. The force, the unit Newton. Newton is equal to kilogram meter per second square. Pressure, we use Pascal, which is equal to Newton per meter square. Energy, work or heat, the unit is joule. Joule is equal to Newton times meter. The power, watt. Watt is equal to joule per second. The electric charge, coulomb, which is equal to ampere times second. We have a resistance here, which is equal to volt per ampere. So you see that these units are so complex. So in order to use these complex units, we just for simplicity use these special symbols. Now let's see how Pascal is derived. You know that the Pascal is the unit of pressure, and pressure is equal to force over area. And force, the unit of force is Newton, and the unit of area is meter square. The Newton is equal to kilogram meter per second square, so over meter square. When the meter cancel each other, I have kilogram per meter second square. So this unit is equal to Pascal. How Joule is derived? Joule, you know that is the unit of energy. So energy, let's say we have the potential energy, which is equal to mass times gravitational acceleration times the height. The unit of mass is kilogram. The unit of acceleration is meter per second square. The unit of height is meter. So I have kilogram meter square over second square. So this is a so complex unit. So I call for simplicity a special unit joule. So 1 joule is equal to 1 kilogram meter square per second square. How watt is derived? Watt is the unit of power, you know, and power is the work done per unit time or the change of energy per unit time. The unit of energy is joule and time is second. As we have derived in the previous slide, 1 joule is equal to 1 kilogram meter square per second square. So when I put this value here, kilogram meter square per second square over second, so I have a unit kilogram meter square per cubic second, which is equal to a special unit watt. Another example show how the given units are derived. State the mathematical formula of the quantity. Newton's law of gravitation states that particles attract each other proportion to their masses and inversely proportion to the square of the distances between them. And this is the formula. Here G is the gravitation constant with a value of 6.67 times 10 to minus 11. Now we are going to find the unit of this constant. Now the unit of force, let's write the formula here again. Force is equal to G times the mass 1 times mass 2 over the distance square. The unit of force is equal to Newton. I don't know the unit of G, so I'm going to write G. The unit of mass is kilogram times the unit of m2 is again kilogram over the unit of distance is meter, so I'm going to write meter square. Here it's given that 1 Newton is equal to 1 kilogram meter per second square, so I can write here kilogram meter per second square. So the kilograms cancel each other and put kilogram and cubic meter into the right side. So I have the unit of constant as meter cube over kilogram second square. So this is the unit of gravitational constant. So I can say that the gravitational constant is equal to 6.67 times 10 to minus 11 meter cube per kilogram second square.